This is the 7th lecture on Introduction to Quantum Computing. So today we'll talk about the circuit model of computation. So we'll talk a little bit about classical circuits and gates. And then we switch to quantum circuits and quantum gates and try to get some intuition about how a quantum circuit is constructed, what it does to a system of qubits, etc. So let's start by thinking about classical gates or classical digital circuits. All right. So as we said in classical computing, data is stored in sets of zeros and ones. So data stored in strings of zeros and ones. And one model for computation is the so-called circuit model, where essentially the computation takes all the data, takes all the zeros and ones, and manipulates and changes these in order to achieve some computational task. So these manipulations in a digital computer are done through a certain number of gates, which transform the bits. So a logic gate, and so far we're just talking classically, this is just classical computer science, is some mapping, right? Some operation that takes, let's say, takes the bit string for k qubits. So if, for example, k is equal 3, this can be something like 001 or 100. So takes this bit string for k classical bits, rather, not qubits, classical bits that can only be 0 or 1, and then maps it to some other bit string. And in general, it can be made of, let's say, L bits. So let's consider a couple of famous ones which serve as building blocks of any computation. So a famous gate is the NOT gate. It's a 1 bit to 1 bit gate. So we represent it like this: a triangle, a circle. So a bit comes into this gate and then a bit goes out. So as you can imagine from the name, it just, if it's 0, it makes it 1. If it's 1, it makes it 0. It just flips the bit. So one way to represent these gates is through something called the truth table. So essentially, we have to specify the output for all the possible, let's say, 2 to the k bit strings of input. So if k is 1, if I just have 1 bit, well, I just have I have 2 possibilities. So a can be 0 or 1. And so suppose a comes here and not a goes out. Then not a, if it's 0, it becomes 1. If it's 1, it becomes 0. Okay, so that's a single bit gate that's used very often in all digital devices and no computations. So then there are 1 to 2 bits, 1 to 2 gates. So another one is the OR gate, for example. So it has a figure. So OR takes 2 bits as input and spits out 1 bit as output. So it looks like this. Um, so 2 bits, let's say A and B come in. And then what goes out is 1 bit. And that 1 bit has let's call it A or B, A or B. So it's going to be 1 as long as at least one of the A's or B's are 1. So this is related to basic logic. So suppose 1 kind of corresponds to true and 0 corresponds to false. So our understanding of or is like when we say A or B, it is true when at least one of them is true, right? A or B is false when both of them are false. When both of them are true, A or B is true. When A is true, B is false, A or B is true because one of them is true. And similarly, if A is false and B is true, A or B is true. So the name truth table kind of has its origins in just a study of logic. So if I want to write the truth table here, now I have 2 bits, A and B. So what is happening? So what are the all possible bit strings? Well, I can have 0, 0, 0, 1, 1, 0, 1, 1. Right? So those are these 4, 2 to the power 2 are all the possible bit strings that my input can take, and the output is just 1 bit. So let's write it as A or B. And so what is it? So in this case, it's 0. And in all of these cases, it's 1. So this truth table defines the operation of that OR gate on 2 bits. So here K is 2, I have 2 input bits, and L is 1, I have 1 output bit. The next one is AND, so it's very similar, except this line is not curved, it's straight. We write like this. So again, A and B come in, A and B goes out. The truth table, let's look at them, 0, 0, 0, 1, 1, 0, 1, 1. So again, if we think of 1 as true and 0 as false, in order for A and B to be true, both of them need to be true. So it's 1 in this case and it's 0 in all the other cases. So when at least one of them is 0, A and B is 0. Okay, so that's another famous gate. These are all classical. The bits are just classical bits that are 0 and 1. So let's draw maybe another one. It's called XOR. So the way it works is, again, you have 2 coming in, 1 going out, A, B, A, X, or B. Now, the truth table for this is truth table here is we get 1 if we have 0, 1, and 1, 0, and we get 0 when they're the same. For 0, 0, and 1, 1, we get 0. So this, you can think of it as the operation of addition mod 2, right? So another notation for this is a circle and a plus here in the middle, B. So we add them. So 0 plus 0 is 0. 0 mod 2 is 0. 0 plus 1 is 1. That's also 1 mod 2. Again, this is 1. 1 plus 1 is 2, which is the same as 0 mod 2. Then there are a couple of others. There's something called the NAND gate, which is nothing but an and a not. So you can draw it like this. Well, first let me, let me draw the notation here. So this is again like the and I put an empty circle here. So that's the notation for NAND, and this is the same as, you know, putting an and then taking the output and putting a not there. So you can imagine what it does is, suppose I have AB, again, 0, 0, 0, 1, 1, 0, 1, 0, 1, 1. So if you take the and here, I'm going to get 1 when they're 1, 1 and 0 in all other cases. So in this case, I'm going to get the opposite of that, which is 1 in these cases and 0 in this case. Finally, there's another one called NOR, which is again an or and a not. That's the notation. So again, A, B. And this is the same as an or followed by a not. Let me also write the notation here. So we're saying A and B come in, and the output is A NAND B. So what is the truth table here? Well, A, B. So if I have 0, 0, or gives me 0, this should give me 1. If I have 0, 1, or gives me 1, this is 0. 1, 0, or gives me 1. So with a not, this is 0, and 1, 1 is again 0. Okay. For classical bits, we can also duplicate the bits. Of course, there's no cloning theorem here. So there is this thing called fan out. So you can have a bit coming in and you can make maybe multiple copies of that. So this operation of just splitting a branch, a bit is coming in, and without making any change, we make a copy. It's called the fan out operation. Okay, so now we have some understanding of classical gates, and these are the building blocks of digital computing, you know, electronic and computer devices. So how does it work? So let's try to do something really simple. Let's try to make use of these to just add integers in base 2. So to add integers, one can construct something called a half adder. So adding, let's say, integers using classical gates. So first, let's define something called the half adder. And so it's a composite gate. There's 2 input, 2 output. And the way it works is we can construct it from OR and XOR, or sorry, from XOR and AND. So let's try to do that. Okay, so suppose I have 2 bits coming in here. I have X and Y coming in. And here I output X X or Y. So let me fan out here, pass it on to this XOR at the bottom. And then here, I can take the Y and combine it with X. So here I do X and Y. So this is essentially X plus Y mod 2, right? I'm doing an XOR. And this is X and Y, so it's only 1 if both of them are 1. And in all other cases, it's 0. So let's call that C. So why is this useful? Well, let's try to add two numbers. So let's go back to, I don't know, first grade or second grade or whenever it was, adding numbers, and they're in base 10. So adding, I don't know, let's do 17 plus 35. So how do we do this? Well, I write 17, I write 35 below it. Then there is this column addition, right? So we add 7 plus 5, that gives us 12. So 12, I break it into two parts, right? We have the first digits, that's 2, and then that 1, which is an additional 10. So think of 12 as 10 plus 2. Gives a 1, and it goes to the next column. So 7 is like 7 times 10 to the power 0. And this 1 here in 17 is 10 times 10 to the power 1. So I have a 10 to the power 1 here from this addition. I put it up here. It's a carryover digit. And then I add 1, 1, and 3. And I get 5. Okay, so we know how to add. And if I want to do an addition in base 2, it's going to be a similar story. So let's add, we can add the same numbers in base 2. So what is 17? It's 1 plus 16, right? So I have a 1 here. Then my 2 is 0, my 4 is 0, my 8 is 0, and my 16 is 1. Did I do it right? So 1 to the power 0, which is 1, 2 to the power 1, which is 2, to the power 2, 3. Yeah, that seems to work. So that's 17. What is 35? So I have a 32 in there, and then I have a 3. So 32 is going to be a 1 after 16, and then 16 and 8 and 4 are 0, and then 3 is 1 and 2. So that's 35 base 2. Okay, so if I want to add these guys, what am I going to do? Well, I add 1 and 1. So the result is 2, which means in base 2 it's 0, right? In the same way that we said this, we put this 2 here, that 2 is 12 mod 10. So I want 2 mod 2, it gives me a 0. But then I have a carryover, right? So whenever it's 1 and 1, when they're both 1, I get a carryover bit. So that gives me a 1 here. Again, I have 1, 0, and 1. I add them up, gives me 2 again. That's again 0. Carry it over here. Then 1, 0, 0 gives me 1. 0 and 0 gives me 0. 1 and 0 gives me 1. No carryover, and 1. So did it work? This is 32 plus 16 plus 4. So 32 plus 20, 52. Yeah, that works. Okay, so this kind of motivates calculating this carryover bit, right? So essentially, this operation is what we do here when we add these 2 bits. So we start from this half adder, we add these 2 bits. So this bit is just x or y, which is their sum mod 2. And then this c, if it's 0, then there's no carryover. The carryover is 0. And if it's 1, which happens only when both of them are 1, well, then I add this 1 over here. So essentially, if I pass 1 and 1 to this half adder, I get a 0 here, and I get a 1 for C. Okay. So now from this half adder, if I want to apply this algorithm, I go to the next step. Now, if I have a carryover, I have 3 bits, right? So I have to work with those 3 bits. So I have now this bit, the second bit of the integers, and then I want to add the carryover to it. So from the half adder, one can make something called the full adder, which does this operation for 3 bits. So the way it works is, again, it's taking what I want it to do. So let's do full adder. And it takes in now 3 numbers. And again, here it just gives their sum mod 2. And here it gives C prime, which is a carryover. So if the sum is, the sum of 3 bits, right, can be 0, 1, 2, and 3. It can't be anything else. The largest it can be is 3. And if it's 2 and 3, then 2 and 3 are this thing, the value mod 2, which is for 2 is 0, for 3 is 1, plus a carryover bit. So if this sum is 2 and 3, I want the C prime to be 1. And if this sum x plus y plus c is 1 and 0, I want C prime to be 0. There's no carryover. Okay, so the way we can do this from the half adder, which we already constructed in terms of an AND and an XOR, is this. So suppose I send in x and y. I do a half adder on x and y. Here, essentially, I have x plus y mod 2. Here is the carryover of this operation. And then this c that's coming in, I combine it with this x plus y mod 2. So here I'm going to get the sum of this plus and this, the whole thing mod 2. So we can think of it as x plus y plus c. So that's this. That's giving me this. If I apply a half adder over here, now here, if I take this output and this output and do an OR here, we can convince ourselves that that's the right carryover. So let's spend a little bit of time just to practice more with truth tables to see why that's the case. So I can try to just draw a truth table, right? So let's do that. So we're saying so let's do x, y, c. Okay, so I have 8 possibilities. Let's write them. So 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. and then 1 0 0 1 0 1 1 1 0 1 1 1. All right, so I don't know, at this stage I can call these like A1, A2, A3. This stage I can call them B1, B2, B3, and then here I have C prime and that. So we can check that it works. Okay, so let's do A1 and A2. So I should only look at so for A1 and A2, I should only look at X and Y, the first two, add them. A2 is the sum mod 2. So I have 0, 0, that's 0, and then the carryover is 0. 0, 0 again. 1. So X and Y is 0 and 1. 1 and 0 again gives me 1 with a carryover of 0. 1 and 0 again is this 1 and 0 again. 1 and 1 gives me 0 with a carryover of 1. Again, 1 and 1 is 0, 1. Okay. So what is A3? A3 is nothing but C. So we didn't even have to write it. I just copied that. 0, 1, 0, 1, 0, 1, 0, 1. Perfect. So that's the action of this first half adder over here. Then the next step is, well, B1 is the same as A1. It's just nothing is happening there. So let's do B1, B2, B3. So B1 is the same as A1. So we have 0, 0, 0, 0, 0, 0, 1, 1. Okay, B2 and B3, what is happening? So B2 is the carryover, B3 is the sum of A2 and A3 mod 2. So 0, 0, 0 plus 0 is 0, carryover is 0. This sum is 1, carryover is 0. This is again 1, 0. 1 and 1 gives me 0 and 1. 1 and 0 gives me 1 and 0. 1, 1 again is 0, 1. 0, 0 is 0, 0. This is 1, 0. Okay, so now we're saying B3 is supposed to be X plus Y plus C mod 2. So let's see. So all zeros is 0. Yeah, this is just 1, 1. Seems to be okay. This is 1, 1. It gives me 1. This is 2 1s gives me 0 mod 2. 2 1s gives me 0 mod 2. 3 1s gives me 1 mod 2. So fine. And then let's do this C prime here, which is B1 or B2. So it's going to be 0, 0, 0, then a 1 here, 0, 1, 1, 1. All right, so we can check that here where we had a 1 plus 1, it's 2, so it has a carryover of 1. And again, these last guys have either 2 or 3 1s, so they give a carryover of 1. So this was a bit of overkill. It's kind of easy to see that we're going to get a carryover of 1 for the total if either this has a carryover or this has a carryover. So if both of them are 0, we should not have a carryover. So this is a full adder. So from the full adder, now suppose we have two arbitrary integers. So we represent them in as binary numbers in terms of a bunch of digits. So so let's imagine, I don't know, let's say one is, let's go back to our example here. 17 and 35, so 1, 0, 0, 0, 1. And 35 was 1, 3 zeros, 1, 1. So we can always add a 0 here to make them have like the same number of digits. So we can call this, for example, x0, x1, x2, x3, 1, 2, 3, 4, 5, 6, x4, x5. And these digits, these bits we can call y0, y1, y2, y3, y4, y5. Okay. So if I want to add these two numbers using a circuit that makes use of these building blocks, so what would I do? I would first send in y0 and x0 into a half adder. So here, this gives me the first digit. Then this is a carryover. So I take the carryover and then combine it with the first digits of the next column, so y1, x1, and I send that into a full adder. So again, now here I'm getting the next digits, that the sum of those three numbers are mod 2, and then I get the carryover here. Now I can take this carryover, take the next two digits, which would be y2, x2, send these three into a full adder, again, get the next digit and the carryover, and we can keep going with this until, until the number of digits in our integers. So that's an example of a classical circuit that's designed to perform a computational task, right? It takes input as a bunch of zeros and ones. It manipulates them in some way in order to produce an outcome that we want. So quantum mechanically, you have to think a little bit differently, because as we said, the bits can now be in a superposition. So we can think of a truth table. We can think of some way that, some operation that does something prescribed on the basis states in the computational basis, which is going to look like these truth tables. But then it's going to apply on some superposition of states. So how should we think of a quantum circuit? So we want to build some intuition about the quantum analog of these digital circuits that manipulate data. So now the idea is to somehow manipulate the states of a bunch of qubits. This calculation, for example, if I have, let's say, I have 2, 1, 2, 3, 4, 5, 6 bits integers, I need to send in 12 bits. I'm going to keep going until I reach like y5 and x5. So that's 12 bits. And that's a circuit, right? that takes in 12 bits. It does some manipulations, and it produces, again, it produces at the end of the day, I believe, well, 7 bits maximum, right? Because you can have a carryover at the very end. So quantum mechanically, again, we imagine we have a certain number of qubits, and then the gates are going to act at various places on different qubits and change their state in some way. So let's think about quantum circuits. So quantum circuits, suppose I send in n qubits, right? So these qubits live in a space of dimension 2 to the n, in the same way that, you know, the n bits, right? If you want to think about n classical bits, if you want to think about their truth table, you get 2 to the n different strings. And to specify the truth table for a complicated circuit, one needs, you know, an exponential number. You need to list all those bit strings and then look at the outcome. We don't do that, right? That's going to be complicated, but we can predict, and that's, you know, that operation is really the result of the calculation. So we build up the calculation in terms of these simple building blocks that maybe take in 2 or 3 bits at a time and then perform some operation, and then you let them cascade, you put them all together, and then it builds a complex calculation. So in the same way, a full quantum circuit takes n qubits, which is going to be a vector in this 2 to the n dimensional Hilbert space, right? As we said, you know, if you have 2 qubits, okay, so the basis states can be 0, 0, 0, 1, 1, 0, 1, 1, and then the state of the entire system can be any superposition of these. So it's a vector that lives in a 4-dimensional space for 3 qubits. It's a vector that lives in an 8-dimensional space. So ultimately, whatever that circuit is, it's going to be, the result of the circuit is going to be some unitary operation applied to the state of these n qubits, and it would output a state, you know, that's different. So the way we build quantum circuits is we apply unitaries as building blocks to generate some unitary transformation on the entire state. So the simplest unitaries, of course, are going to act on 1 qubit. So here, so the gates, the classical gates we talked about, most of them were acting on 2 and producing 1. They had this knot classically that was taking 1 and just flipping it. There's nothing else you can do. So quantum mechanically, of course, we can't change the number of incoming and outgoing, right? We can ignore a certain number of qubits, but essentially we have the same number of bits coming in and the same number of bits going out. That's the system. All right. So let's talk about single or 1 qubit or single qubit. So these are unitary operators that take a qubit and output. So take the state of a qubit and change it to some other state. Again, here you can have, for example, you can have maybe alpha 0 plus beta 1 coming in. And then here we're going to get something else. So in general, we're going to get, if U is some 2 by 2 unitary matrix, I'm going to get U times alpha beta, whatever that is. So let's write it explicitly. And then the first element multiplies 0, the second element multiplies 1. So there are a bunch of important and widely used single qubit operations. So one of them is, for example, the X operator, which has a matrix 0, 1, 1, 0. So what does it do? Well, I can see easily what it does to basis states. So X times 0, right, is going to be 0, 1, 1, 0. 0 is the first basis state. So its representation is 1 and 0. So this gives me 0 times 1 plus 1 times 0 is 0. 1 times 1 plus 0, 0 is 1. So this is the same as 1, right? So it flips the qubit. So if the qubit is 0, you get 1 out of it. And if the qubit is 1, again, it flips. So that's going to be now 0, 1. And then if I do this, I get 1, 0. So that's the same as 0. So it's somehow like the NOT operation. It changes the state. But of course, these are qubits, right? So the state is not just 0 and 1. So a general state would be alpha 0 plus 1 plus beta 1. So suppose I put this X gate and I send one qubit that's alpha 0 plus beta 1 for some arbitrary alpha and beta, as long as it's normalized. The way it changes that state is it gives me alpha 1 plus beta 0. Now, of course, the quantum computer doesn't have one qubit, so this is going to be part of a big, like many qubit state. So suppose there are other bits that are there and go through, and suppose at this point some superposition of these is sent. So basically, like, one can think of the state here as some superposition of various tensor products, right? So you have tensor product of 0 with some stuff living in the Hilbert space of other bits, and some tensor product of 1 with some other stuff on the other bits. So this goes in and just flips the 0s and 1s there. So let's do an example to make this idea a bit more explicit. So suppose, let's say I have 2 bits and I have an X here. So this is the first one, this is the second one, say A and B. They go through. So I don't know, let's imagine the input here is, let's do 1 over square root 3, 0A, 0B. So I write it as 0, 0, plus, let's do 1 over square root 3 here. Plus 1 over square root 3, 0, 1, plus 1 over square root 3, 1, 1. So suppose that state is sent into this operation. So essentially, the way it works is it acts as the X, which flips on the A qubit. It doesn't do anything to the B qubit, so it acts as identity on B. So what is it going to do? So what is the 2 qubit state over here after the application of this 1 qubit gate? Well, I'm going to look here and see what happens to this 0, 0. Well, the 0 flips, so it goes to 1 over square root 3, 1, 0, plus 1 over square root 3. Now this 0 flips. The state, for B, nothing happens, so that becomes 1, 1. And this becomes 0, 1. So this state, let's say in the basis of 0, 0, 0, 1, 1, 0, 1, 1 is 1 over square root 3, 1 over square root 3, 0, and 1 over square root 3. And this state, the output state, is going to be, I don't have the 0, 0, and everything else seems to be 1 over square root 3. So that's how this thing, this 2 qubit gate, which is essentially a 1 qubit gate, but it's acting on 2 qubits, transforms the state of 2 qubits. So essentially that should be a unitary acting on this 4-dimensional space, if you wish. And we know the unitary for the first guy. So the way I construct this, so suppose I have this coming in, there's an X over here, this coming in, nothing happening. So the action on the first bit is going to be X. The action on the second bit is going to be the identity. So the action on the tensor product of these bits is going to be X tensor identity. So if I want to draw this, I have my X, which is 1, 1 on the off diagonal. I tensor it with an identity. 1, 1 on the diagonal. So this gives me 0, 0, 0, 0, 1, 0, 0, 1. So I put an identity here. Here I have a 1, I put an identity. Here I put 0, 0, 0, 0. So that's the action. And then we can check easily that, on any state for 2 qubits, it acts as it should. So as an example, if I take this and multiply it by this input here, zero, 1 over square root 3, what does it give me? So the first row picks a 0, where it's a 1, that's 0. Second row picks this picks this, and this also picks that. So it works. Okay, so we have a whole bunch of single qubit gates, and then of course, when you have a system of multiple qubits, that's how they combine. And then maybe later, so it's like level 1 here, and then maybe later I put something over here, then it acts as a non-trivial gate on the second bit and as an identity on the first one. So so these serve as building blocks for constructing more complicated unitaries for multiple qubits. So another kind of famous unitary is the Y, which is very similar to X, but it has a minus I and an I here. So yeah, let's see what y does on 0, for example. So it's going to be 0 minus I 0, acting on 1, 0. So that gives me 0 and I. Y acting on 1, 0, 1. This gives me minus I and 0. So it flips, but it also gives some relative, gives some different phase factor. So it gives a relative minus sign. Another famous one is the Z gate. So that's just 1, 0, 0, minus 1. There's a gate called the Hadamard gate. You can construct many different one qubit gates. There's another famous one called the S gate. So S is 1, 0, 0 I. There's another one called the T gate. And as you can imagine, like any 2x2 unitary matrix can be a gate. So there's an infinite number of unitaries, and they change continuously. It's just some of them are they can allow some kind of universal computing. So these are useful to have in mind. But yeah, we'll continue this discussion and talk about 2-qubit gates, control gates, try to play a little bit more, construct some circuits. So I think that's a good place to stop, just as some very brief introduction to quantum gates and quantum circuits. And we'll continue this discussion next time.